Hello all, in this video we're going to go ahead and take a look at the difference between discrete versus continuous graphs, and also take a look at how to determine if a table is going to be linear versus it being nonlinear. So let's go ahead and get started, ladies and gents. So a discrete graph has a pretty cool characteristic. It will be a graph that has a series of isolated points, like what we have right here. So discrete graphs always will portray this isolated set of points that are taking place. Most of the times with discrete graphs, we can think of them as having like counting whole numbers that are easy to work with, that we're allowed to count basically on our hands and fingers. While continuous graphs are going to be a continuous line of sorts. So for instance, something like this line right here would represent a continuous graph. So all points that fall on this line, there's an infinite amount of points that fall on this line. So they're all connected to each other, representing a continuous graph. So in this case, we can say like all points are connected to each other. Connected. There we go. Now, you do have time where we have some graphs that meet characteristics of both of these. And in that case, since the graph will have characteristics of both discrete and continuous, we will classify those as neither of the two. So let me go ahead and give an example of what that might look like. So this would be a graph that we would classify as neither. If I have a set of axes, and this set of axes has character traits of both continuous and discrete. So maybe we have like a discrete point here, a discrete point there, but then we have parts of it that's continuous, like here or down here. We can go ahead and see that there's parts of this that's continuous and parts of it that is discrete. So since it has traits of both of those, we would simply classify a graph like this as neither. Now, for the second part of this video, we are going to go ahead and take a look at what exactly makes a function linear. So we're going to take a look at some of the fundamental, and that is being able to take a data set or a table and determine if it's linear or not. So for my first example here, I'm going to go ahead and write a table like so. I'm going to go ahead and fill it in with some data points. Okay, so in order for a data set or a set of points to be considered linear, it has to have what we call a constant value or a constant ratio. So we need to be able to determine how to get that ratio from a data table. So what we need to do is we need to take a look at the difference of the y values over the difference of the x values. So we're going to go ahead and take a look at the difference between our y values first. So we're looking at from 6 to 11, this interval, what is the overall change here? So from 6 to 11, this is an increase of 5. From 11 to 16, this is also an increase of 5. From 16 to 21, again, that is also an increase of 5. Now, I'm going to go ahead and also look for my difference of x values. So let's go ahead and take a look at that. So I'm going to start off with my first interval between 1 and 2. The change from 1 to 2 is plus 1. The change from 2 to 3 is plus 1. And the change from 3 to 4 is also plus 1. So now when I look at this ratio, for every interval or every change of y that I have, I want to correlate that to a change in x. So my first change of y was 5. My first change of x that it is correlated to is this 1 over here, and it went up by 1. Now I want to see, does that match with the rest of my intervals that are here? Well, it does. This next point has a change of 5 as well for my change of y. So I'm going to go ahead and separate that. And then my change of x was also a 1 as well. And then my last one from 16 to 21 was also a change of 5. And then my change of x from 3 to 4 was positive 1. Okay, now sometimes we do have to simplify all these numbers that are take place, but in this case, everything is simplified. 5 over 1 is just simply 5. So that is going to give a ratio of 5 to 1 every single time. So that makes this particular scenario linear. So as long as this is constant, that we once we simplify the values, then we have a linear function. All right, let's go ahead and take a look at a nonlinear function. Let's go ahead and take a look at the difference. So a nonlinear function, since I already kind of gave this one away, a nonlinear function will lack the constant ratio that the other one had. So let's go and take a look at one. So I'm going to go ahead and write down my first table of values. And now I'm going to go ahead and start trying to look for my change in y over my change in x. So from 16 to 8, that's a drop of 8, or a minus 8. From 8 to 4 is a drop of 4, or minus 4. From 4 to 2 is a drop of 2. Okay, now let's go and take a look at my change of x's. From 4 to 5 is plus 1. From 5 to 6 is plus 1. From 6 to 7 is also plus 1. So when I go to take a look at my difference of y over my difference of x, you're going to notice something different in this one than our last one. So my difference of y of my first interval was negative 8. My difference of x in my first interval was positive 1. Now I'm going to compare that to my next one. My change of y in my next interval was minus 4. It went down 4 units. My change of x in my next interval was a plus 1, or an increase of 1. Now my last one here, my last interval between 4 and 2 was going to be a drop of 2. So a drop of 2 over my interval that it corresponds to for x is an increase of 1. Okay, now these don't need to be simplified either, these values, but in this case, notice how all the values, when completely simplified, are not the same ratio. So these do not have the same ratio, so therefore it's non-linear. So I'm going to jot that down. Not the same, or not a constant ratio. So this is going to be non-linear. Hey, ladies and gentlemen, in the last segment of this video, I'm going to pose 2 different tables. If you would like to pause the video, try them on your own, and then continue the video to check your answers, you may do so. Hey, let's go and take a look at our last 2, ladies and gents. So, here's my first table. That one came out kind of diagonal there. That's okay. It'll still work. Okay, let's go ahead and put a look at the other one over here. Trying to make that one a little bit straighter. If you would like to see this worked out, go ahead and follow along with the video. Alright, so one of my tables here is linear, the other one is nonlinear. So I'm going to start with my table on the left to go ahead and start determining if it's linear or nonlinear. So I'm going to check my interval here between 6 and negative 2, look at my change of y. So from 6 to negative 2, that is a drop of 8. From negative 2 to negative 14, that is going to be a drop of 12. From negative 14 to negative 18, that is going to be a drop of 4. Okay, so now I'm going to compare that to my x's. From negative 2 to 0 is plus 2. From 0 to 3 is plus 3. From 3 to 4 is plus 1. Now I'm going to take each of my change of y's and compare that to its corresponding change of x. So my first change of y over the first interval was negative 8. My first change of x over the first interval was positive 2. My second change of y was negative 12. My second change of x was positive 3. My last change of y was negative 4. My last change of x was positive 1. Okay, notice how all of these can be simplified, well, except for the negative 4 over 1, but we can simplify negative 8 over 2 to negative 4 over 1, negative 12 over 3 to negative 4 over 1, and we already have this one simplified, negative 4 over 1. So that makes our first example here linear. Okay, so this is going to be a linear function. All right, let's go and take a look at our second one here. So I'm going to start off by getting my change of y's. So from 4 to 1, that is a drop of 3. From 1 to 4 is an increase of 3. From 4 to 9, that's an increase of 5. Now let's check my change of x's. From negative 1 to from negative 2 to negative 1, that is an increase of 1. From negative 1 to 2, that is an increase of 3. From 2 to 3, that is an increase of 1. So now if I compare these ratios, my first interval for y's, the first change was negative 3, where the first interval over the change of x was positive 1, so over 1. My second interval over y was an increase of 3, and then my change of x for that corresponding interval was positive 3. My last change of y was an increase of 5. Corresponding to the change of x for that interval is a change of positive 1. Alright, now looking at all these are easy to see that they are all different ratios. They do not simplify to be the same ratio, so that means this is going to be a non-linear function.